Hey everyone, so today's lecture we're going to talk about functions. Now that we have a general understanding of sets, we can build on that and look back at functions in a much more general way, considering we have some experience with functions from the prerequisite knowledge we came in before this class. So formally, what is a function? Well, a function from a set A to a set B is a rule that associates with every element little a of the set A to exactly one element little b of the set B. So that's one way to say it. And a function from A to B is also called a mapping from A to B. Now, more formally, we can actually define functions as a special kind of relation. And later on in this course, we'll actually come back to relations in the next chapter, actually. But so another way to think about this is if you give me two sets A and B, a relation from A to B is actually just a subset of their Cartesian product, which we just learned about. So you just take a bunch of pairs where the first coordinate is A and second coordinate is B, and in general we call that a relation. And a function is just a special kind of relation. So a function or mapping from A to B is a special kind of relation, and you can call it little f, and you could just say little f is going to be a subset of A Cartesian product B. So it'll be, this right here tells you it's a relation by definition, but it'll satisfy an additional condition, and the additional condition is the same as what we set up here. So in which for every element A of big A, so every element of the set A, there is a unique element of the set B such that this pair is an element of our function f. Right? Now, a lot of times you usually don't write you don't write it like this, but you can always write out your functions in terms of these pairs if it's possible to even list them. So some other notations that are common, you could write your function like this. You could say f and then colon A to B. This kind of designates where your inputs are coming from and where they're going to. You could also write it like this, and then instead of writing pairs, ordered pairs of elements like this, you would usually write it in this way. So you'd say f of A is equal to B, and that's how you would read it. You might see in the literature occasionally it written like this, where it's kind of saying A is going to get mapped to B via this function f. But I would say that this right here is probably the most common one, and you're probably familiar with this version of it in some of your other classes. Okay, so let's look at a specific example. So let's say that I just give you two sets, A and B. So let's say A has the elements A, B, C, D, and B has the elements 1, 2, 3, 4, 5. So what could a function look like given this situation here? Now we're dealing with something much more general. Now in previous courses you might have seen your functions given as some kind of rule, but in our situation we could just kind of write it out in terms of sets. So we could define our function using the original definition, which is kind of giving these pairs, right? So one way you could define it is let's create a function. Okay, so for example, I could say f is the function given by some ordered pairs here. So I could say, okay, I'm going to map A to, let's just make it really simple. I'm going to map A to 1. I'm going to map B to 2, I'm going to map C to 3, and I'm going to map D to 4. I could map it to 5, but let's just have kind of a nice pattern. So this is one way that you could write your function. You could also write it like this. You could actually just individually write out what are those inputs going to. So I could write f of A is 1, f of B is 2, f of C is 3, and f of D is 4. Right? Another way that you could actually write all this out is you could use what's called an arrow diagram. So what you could do is you can actually make your set A over here, and you could label them. So I could write A, B, C, D. Okay, and then I could create my set B over here. And label these 1, 2, 3, 4, 5. Okay, and This is my set B. Okay, and then to designate these pairs, what I could do is I could just I could draw arrows. Okay, and the arrows are going to tell me where the inputs get mapped to. So A, I said that would get mapped to 1. I said B got mapped to 2 here. And C gets mapped to 3. And D gets mapped to 4. Okay, and this is what's called an arrow diagram. Okay, so this would be 3 ways that you could kind of write out an example of a function. There are many, many functions from A to B, right? One question you could think about actually is how many total legitimate functions could you create? One thing to keep in mind is note that this number 5 here, which is an element of B, was not hit by anything. There was no input that actually got mapped over to 5, which is perfectly fine. Our original definition only requires that everything in the domain, so everything in A, has to get mapped somewhere. Okay, so as long as you have arrows coming out of A, you know, and there's only one, right? You also can't have like multiple things come out. Okay, so this would be a function. Why don't I give you an example of something that is not a function? So let me change the color back here. So f is a function. Okay, so let's try to create something that is not a function. Okay, so what if I instead, maybe I'll define something that is a relation but it's not a function. So for example, let's just call it R1. So what I could do is I could have A gets mapped to 1 as a mapping, but as a relation, remember a relation, it just has to be a subset of A Cartesian product B. So I could have a relation where I have this pair, A1, but then I could also have the pair, there's nothing stopping me from making the pair A2, for example. Okay. Now, you can draw arrow diagrams for relations. So for example, right away, I can already say that this is not a function. Okay, but it actually is a relation. But it is a relation, and the reason for it being a relation is as long as I'm a subset of the Cartesian product of A and B, then it is a relation. So over here, F is also a subset of the Cartesian product of A and B. So it is a relation, but it happens to satisfy this additional condition that we're requiring. This actually fails 2 things. Okay, if you think about it, it fails the condition that says everything in A has to get mapped somewhere. Okay, and it has to get mapped to a unique B. So it actually has 2 problems with it, right? If I draw, maybe I can illustrate this a little bit better if we try to draw the arrow diagram for this one. So arrow diagram, you would start out the same idea, A, B, C, D. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and then my arrows, I'm just sort of kind of have a pair A1 here, but then I also have a pair A2. Okay, so there's 2 problems with this. With a function, you can't have an input, so to speak, go to multiple things. Okay, so I can't have multiple outputs for a single input. That's a problem. Second thing that there's a problem is not everything in A was mapped somewhere to B. Okay, so for example, do you see that I have B is not associated to something, little b here is not associated to an element of the set big B, right? C didn't go anywhere and D didn't go anywhere. So that's another problem, because if you look at this definition, it's a special kind of relation. F has to be a special kind of relation in which every element of A, there will exist a unique B, all right? And that failed, right? Okay, so you got to look out for that. You can't have everything in the in this set A has to get mapped somewhere, and you also have to make sure that each of the inputs only has it's only going to one unique element over here. All right. Okay, so let's look at some examples, right? So in this next example, let's write each of the following functions as a set of ordered pairs. So this first function here, it's probably written in a way that you're more familiar with. So you have this function f, which is going from the reals to the reals. Okay, so you're inputting a real number, and it's going to give you a real number. Okay, and the rule is that we're going to take the input and we are going to square the input. Okay, so write it out as a set of ordered pairs. Well, okay, so what would these ordered pairs look like? So f would be a collection that would look like this. You'd have x, and then you would have x squared. So you could write it like this. Okay, so just to kind of illustrate that a little bit, you could look at some specific examples. So for example, f of 0 would be 0 squared, which is 0, and that's giving you the pair 0, 0. So you see it's of this form, right? 0, 0, where 0 is an r. If you were to look at 2, for example, this rule would give you 4, and that's giving you the pair 2, 4. So you notice that this is 2, 2 squared, and so on. Okay. Now I'm writing it in this way using set builder notation because it's actually impossible to legitimately list all these elements out because these are real numbers, and that's yeah, it's not possible. We'll talk about that a little bit later as well. Okay, what about the next set? So the next set, you have real numbers going to, and this is the set of positive reals, and then unioning it with 0 as well. This is allowing 0 or positives, right? So this again was positive real numbers. So unioning this with 0, this would actually be non-negative, right? Non-negative real numbers. Okay. So again, your input is a real number, and then your output is non-negative real number. Okay, which is actually the same as up here. It's just what actually changed is your allowable outputs. Okay, so I have x, and then I'm going to have x squared again, and x is a real number. Okay, and this x squared is definitely greater than or equal to 0, so we are okay. All right. Now, if it happened to be that this second, the x squared was not in this set, then it would fail to be a function. You see that there may be an input that's going to an output that's not in this set, and that would not be a well-defined function. In other words, maybe I should just illustrate it with, we're able to legitimately make the claim that this is a subset of the Cartesian product, right, of reals and real plus union 0, right? So in other words, the first coordinate is a real number, second coordinate is definitely going to be a non-negative real number. Okay, and then up here, we definitely had that this was a subset of real Cartesian product real. Okay. Now, another type of function that actually comes up quite often in computing are these two functions. So the floor and ceiling function. So floor function is effectively you round down. So if I give you a real number, x, the greatest integer that is less than or equal to x is called the floor of x. You denote it like this. You have sort of the, I don't quite know how to describe this. It looks like a elongated L and then a backwards elongated L. So the little Yeah, so that's just the notation. And then the ceiling function, it's sort of you're rounding up. So if I give you a real number, you're going to find the least integer that is greater than or equal to x, and the notation for that looks like this. So comparing it to the floor, I can kind of explain it a little bit, right? If you have the parts going in are on the top, that's the ceiling, and down here it's sort of indicating the floor, right? So you can guess the name, why it's given that name. But anyway, if I give you the number like 3.4, for example, this is the floor, so that's just reminding you to round down. So rounding this down, this would be 3, right? So this would be the greatest integer that is less than or equal to x, right? There are many integers that are less than this, right? 2, 1, 0, -1, so on and so forth. But the greatest among those would be 3. So this is uniquely defined. So you see the floor function. In other words, one way you could actually kind of write that floor function is you could think of it as, okay, I have this input that's going to go here where this dot is, and you give me a real number, and then this is going to give you an output that is an integer, right? Because you see the way that it's defined is you're finding the greatest integer that is less than or equal to x. So the input will be a real, and then the output will be integer, right? So here's your example. Okay, so what about 3.4 in the ceiling? So now rounding up, this would be 4, right? And then similarly, the ceiling is also a function. You can think of this as a function from reals to integers as well. Okay, what about -3.4? Well, if I'm going, this is the floor, right? So I'm going to round down. So this would be -4, right? Because it has to be an integer less than this. So now negatives, right? So -4 is less, -5, -6, but the greatest among those would be -4. And then rounding up, this will be -3. Okay, so those are some basic ones just to think about positive and negatives. Let's do something a little bit more complicated. Okay, well, I'm going to take the floor of this expression here. So I'm going to take the ceiling of a third plus the ceiling of 2/3 minus 2/3. Well, we can break that down in a couple problems. So the ceiling of a third, so rounding that up 1/3, you would get 1. Okay, rounding 2/3 up, you would get 1, and then subtracting 2/3. Okay, so what do we get inside this? So this would be the floor of, so 2 minus 2/3 would be 1 and a third, right? So that would be, what, 4/3? Okay, so you add that up, and then what would the floor of this be? So it's 1 and some change, right? So 1.33333, so on and so forth. So rounding down, the floor of that would actually be 1. Okay, so that would be the answer. Okay, now some more definitions. Oh joy, right? So if I give you a function from a to b, we call a the domain of the function, and we call b the codomain. You're probably familiar with hearing the terminology for the domain, but the codomain is just where the outputs live. Okay, we'll talk about range in just a second. You probably have heard of that as well, but domain is where your inputs live. Codomain are where your outputs live in general. Okay, and you can also write it like this. Your book tends to use this terminology. For the domain, you can abbreviate that as DOM of the function, and then for the codomain, you could write co-DOM of the function for b. Okay, now some other terminology. So if you give me an element of the domain a, and I map it somewhere, so f of a is equal to little b, this little b, we call that the image of little a under the function f. And then similarly, what you can actually do is you can look at an entire set. You could actually take an entire set S, and that could be a subset of A, and you could look at what its image looks like. Okay. Let me try to draw. Maybe I should draw some pictures for you for this. Okay, so let's draw some pictures that I think will help illustrate this. So basic picture I could just draw for you is, okay, if I have A and I have B here, okay, and I have little a, all right, little a is going to get mapped somewhere inside of, so every element of the domain has to get mapped somewhere if it's a function, and this will get mapped to some b, and we'll call that f of a. Okay, so this little b, we call this the image of little a. Right, that's what this first thing is just saying. So we call this b the image of a under this function. And then similarly, I could give you a whole entire subset of a, and we could look at its image. Right? So the image of s is actually an entire set. We call it f of s, and you're looking at the collection of all of the images. Okay, so in set builder notation, we just write it like this. So f of s, the image of the set s, would be f of little s for each little s that's in the big set S. Okay, it's probably easier to illustrate that using maybe a picture. So comparing it to this picture, if I just draw it again. Okay, so here's A and here's B. Okay, so you're going to have some set S that lives in here. So here's your S, that's a subset. And everything in here is going to get mapped somewhere. Okay, so I could have this get mapped here. I could have this get mapped maybe to that same element, and then here. And the collection of things over here in B that are actually hit, this would be f of s. Okay, so each of these are like your little elements of s. You can call it s1, s2, s3. And this is your collection of outputs specifically looking at s. So we would call this the image of the set S. Okay. So if I give you, again, if I give you a subset S of A, we call it, then the set f of s is the image of s under the function. And in set builder notation, we'll write it like this. If you look at the largest subset we can have, which is all of A, and we look at its image, that's actually called the range of the function. So the range of f, or the image of f, is the set of all images of all the elements of A. So in other words, that's just like a formal way of saying the collection of all the outputs of the function. And if you give me f as a function from a to b, then you could write the range or the image like this. You could write f of a, you could call it the range of f, you could call it the image of f, and in set builder notation it would just look like this, f of x, such that x is an element of a. So let me give you a picture for that one. So it's sort of a blown up larger version of this. So if I have, here's a, and here's b, okay, then everything in A has to get mapped somewhere. Okay, let's say that these two get mapped to the same thing, just so that way the picture. You know what? Maybe I'll use a different color to illustrate that. Okay, so this collection right here, this is the range of f, also called the image of f, and also you could write it as f of a, because you're effectively doing the same thing that you did up here. You're just actually doing the entire set. You see, if s was all of a, the picture would look like this instead. Okay, so yeah, hopefully that picture kind of illustrates it a little bit. You could have things left over. Maybe I should add that in. You could have things down here, okay, that are left over, that are not hit. Just like our original function. If you go all the way back to our original example that we had up here. Do you remember this example, this very first function? Did you see that the number 5 wasn't hit, but we still had this legitimate function? So the range, you see the range would actually just be the numbers 1, 2, 3, and 4. Those are the collection of outputs. Those are actually the things that are hit. While the codomain is just where the outputs live, which would be this B set here. So it's in general, it's bigger. Okay. Okay, so that's the range. And what else do we have? Okay, well, if I give you a b in the codomain, then the set of elements of A which map to B is actually called the preimage of B under the function f. All right, so let me see if I could draw a picture of that for you. Well, so this is a little bit more general. Well, it's just a different kind of picture. It's not that it's more general. It's just probably a little different than what you've seen before. So now, unlike before, if I'm up here, the picture is if I give you A, everything in the domain has to get mapped somewhere over here. Okay. If I pick something arbitrarily in the codomain, okay, little b, there may or may not be something from A that hits it. Okay, so there may be nothing that actually hits this element B, just like the number 5 in that very first example that we were just looking at, right? But sometimes there are elements that hit it. So if there are elements that actually map to this B, okay, then this collection, we call that the pre-image of little b in B. The notation for that can be a little misleading. Sometimes you actually you write it like this. Okay, I'm not actually talking about an inverse function. We'll talk about inverse functions a little bit later, but in general, this is a set. You could write it out in set builder notation. You're actually looking for the elements of A such that f of A is equal to little b here. So you see that each of these are like, I have an A1, A2, and I have an A3. All of these get mapped to B. Like this is f of A1 equal to f of A2 equal to f of A3. Okay. So the preimage is a set, the preimage of an element in the codomain, and this set can be empty. There may be nothing that maps to this, okay, or there may be something, okay. So if you actually go back to that first example again, right, the preimage of 1 was A. It's the set containing A, right? It's the collection of all the inputs that get mapped to it. Preimage of 2 would be the set containing B. This would be, it's set containing C. For 4 would be set containing D. And the preimage of 5 would be the empty set because there is no element of the domain that gets mapped to 5. Or yeah, so preimage is a little bit strange when you write it out by definition, but you can kind of see why you might want to consider that if you're looking at domain versus codomain. And in general, you can kind of play the same game, and you could pick an entire subset of the codomain, and you could look at the preimage of that entire set. You could draw a picture for that, but I think it's good to just get an idea of how it works for the elements, and as we progress, maybe I'll come back and draw you a picture for the more general situation. Okay, so let's calculate some things. Let's look at a specific example. So suppose that I give you f, and it goes from R to R, so real to real, and it's defined algebraically in this way. So f of x is 5 times x squared minus 2, and then let's define two sets. Let's say S is the set containing these 4 numbers, so it has -3, -1, 0, and 3, and t is this interval from 18 to infinity. So in other words, t is the collection of real numbers that are strictly greater than 18. All right, so here's a series of questions just asking about the definitions that we just learned up above. Okay, so what's the domain of the function? Well, the domain of the function is where do the inputs come from? Okay, so the domain of the function is where do the inputs come from? So this is reals, right? Then the next question is what is the codomain? Okay, well, the codomain is where the outputs live. Okay, so that is the reals. Okay, and then the next question is what's the range? Okay, so again, remember that the range of f, so the range of f is you're actually looking at the collection of outputs. Okay, so what will this look like? Well, by definition, this will be f of x such that x is an element of the domain. Okay, so just going back up to the set builder notation that we had for what the range was, right? So we said that the range was the collection of outputs. You could write it in set builder notation this way. So we could simplify it using our set builder notation, and it looks like this. Well, now I know what f of x is. It's defined algebraically in this way. So I could just write 5x squared minus 2, sorry. So just replace it with this, such that x is a real number. Okay, now this is an answer, but is there a better way that we can kind of classify that a little bit? I mean, can you tell me a little bit more about what these outputs look like? Well, we know that really what you're just doing here is you're taking x squared, you're multiplying by 5, and you're subtracting 2 from it. So let's kind of explore that a little bit. If I start with x being a real number, right, then I actually know that if I square it, it is not just an arbitrary real number, right? I actually know a little bit more information. Don't I know that when I square something, it's definitely non-negative, right? It's either 0 or positive. So when I square a real number, now it's going to be greater than or equal to 0. And could I use this to get a little bit more information? Well, if I multiply both sides of this inequality by 5, do you agree that 5x squared is greater than or equal to 0? Right? I can just multiply both sides of this inequality by 5. And then now I could subtract 2. All right, sorry about that. I accidentally forgot to silence my phone. Okay, so what if I subtract 2 from both sides of this? So then we get this expression. So we have 5x squared minus 2 is greater than or equal to negative 2. Okay, well that actually does help us, because look, this is the expression we're looking at. And we're saying that it's going to be the collection of these expressions such that x is a real number. So really, I'm guaranteed now that all of these are greater than or equal to negative 2. So in other words, do you see that I could actually just write, you know what, let me use a different variable. Let's say I'll call it y now, such that y is real and y is greater than or equal to negative 2. Right? Because look, I'm just saying that this expression is greater than, I solved it, it's greater than or equal to negative 2. You could write it in interval notation. Another way you could write that is you could write negative 2 to infinity, and then use the square bracket to mean that you would include this. Right? So you would want things that are greater than or equal to negative 2. Okay, well that's one way to describe the range. And you know what? Another thing, maybe just for the sake of completeness, look at this. So your codomain was all reals, right? So and our range that we just calculated is this collection, right? So I have negative 2, and I'm going to look at specifically. Okay, so this is our range of f. I'm just pointing this out to illustrate the fact that the range will always be a subset of the codomain, right? So do you see that this collection lives, the collection of outputs lives in the reals. So the codomain may have things in it that are not hit, right? So for example, there is no for example, negative 10 is in the codomain, right? But there's no input that'll give you a negative 10, right? Once I plug in an input, from the work that I've done, I know that they're all greater, the outputs are all greater than or equal to negative 2. So it's impossible to hit like negative 10, for example. Okay. Now, what is the image of negative 3? Well, by definition, all that's really just saying is what is f of negative 3. So we could do that pretty easily, right? So just plug in negative 3 for x. So you would say that this is 5 times negative 3 squared minus 2. So just do a little bit of arithmetic, right? So 5 times negative 3 squared is 9. And then, so what is this? 45 minus 2. So 43. Okay, not too bad. All right, then now what we want to know is what's the image of S? Well, S had several things in it, right? It had these 4 things in it. So we have to figure out what is the image of each of these. Well, we already figured out f of negative 3, right? We already have that one. So we just figured out f of negative 3. So let's figure out f of each of the other ones. So negative 1, 0, and 3. So negative 1, 0, and 3. So negative 1, 0, and 3. Okay, so this will be 5 times negative 1 squared minus 2, 5 times 0 squared minus 2, and 5 times 3 squared minus 2. Okay. Okay, so this will be 5 times 1 minus 2. So 5 minus 2 is 3. Whoops. This will be 5 times 0, which is 0. Okay, minus 2. So 0 minus 2 is negative 2. And then this one is 5 times 9 minus 2, which we already calculated that, right? Which is 43. Okay, so taking into account all of these things, so f of s would be the collection of so it would be the collection of outputs specifically considering these inputs, right? So with these inputs, you would have the set containing each of these outputs. Now, if I specifically wrote out the list, I'm going to have repeats, right? So the set of these, right, I have some repeats here. So I don't write that repeat. So it's actually just going to be 43, 3, and negative 2. Right, so this would be the image of S. Okay, and then finally, let's look at some of these pre-images, right? So what's the pre-image of 18? So by definition, this pre-image, okay, of 18 is you're going to look for things in A such that f of A is actually equal to 18. Okay, so let's kind of look at this. You're looking for things where the output is actually 18. So you're really solving for that, right? So you want to solve for when f of A is equal to 18. So solve f of A is equal to 18. So what's f of A? Well, f of A will be, if you plug in A for x here, so this will be 5a squared minus 2. So 5a squared minus 2 equals 18. You don't have to use a, you can use x just as above. It's not that big of a deal. Okay, and then solve for this. So add over this, you'll have 20, then divide both sides by 5, you have 4. Okay, and then if you take square roots, you have to be careful that you have plus or minus, right? You're going to have two solutions when you take square roots, right? Because technically, if you take the square root of the left, you get an absolute value. That's the reason you'll have two solutions. So this will be plus or minus 2. So there's only two possible a's. So this will be so solving this, we just did that over here. A is plus or minus 2. So and A was big A was real numbers. So if I just write that out, if I just say A is a real number such that A is equal to plus or minus 2, well, what's in this set? Just those two numbers, right? Plus 2 and minus 2. So that's the pre-image. So again, the pre-images, these are the inputs that would give us this as an output, 18 as an output. So these two inputs, if I plugged in 2 into the original function, right, if I plugged in 2, I would get 18. And if I plugged in negative 2, I'd get 18. And there are no others, right? So you're sort of classifying what inputs get me to that output. So you're actually kind of familiar with doing that in some situations, right? Finding roots, you've done this, and in other scenarios, you've done this before. It's just we're doing things in a much more general setup. All right, now finally, what's the pre-image of the entire set T? Okay, so the big set T is real numbers that are strictly greater than 18. Well, the nice thing is that you just figured out what's the pre-image of 18. Okay, so if you're trying to figure out what's the pre-image of everything greater than 18, it's going to follow a pretty similar result here. Okay, so let's start to write that out. Now, as a definition, you could write this as follows. You could say the pre-image of T will be elements of A, so it'll be pretty similar to this, But instead of saying f of a is equal to 18, you would say f of a is an element of the set t. And what does it mean to be in t? Well, t is this interval, right? This interval from 18 to infinity. So in other words, you're looking for things that are strictly greater than 18. Okay, so you have elements. So a is a real number, right? And you want f of a. So what was f of a again? So that was 5a squared minus 2, and you want that to be an element of t. Okay, another way to say that is you want this, if you want it to be in t, it would have to be strictly greater than 18. So really the goal is to solve this inequality, and you could do that pretty similar to what we did over here. So solving this inequality, you have to think back to some of our prerequisite knowledge again. So 5a squared minus 2 is greater than 18, so add the 2 over, so 5a squared is greater than 20, divide both sides by 5, and you get this. And then now you just have to be careful with inequalities like this, and when you take the square root, you will have a is greater than 2, but then you could have the negative 2 situation. Okay. Now, if you're thinking about a, if a, it's actually going to have to be less than negative 2, right? Because if I'm less than negative 2, such as negative 3 or negative 4 or so forth, when I square those, then I will be greater than 4, right? Negative 3 squared is 9, which is greater. Negative 4 squared is 16, which is greater. But if I was to write that this was bigger, then that would be a problem, right? Because then I would have like negative 1 or 0, and squaring those is not necessarily satisfying this. So just got to be a little bit careful when you're taking square roots with inequalities. This actually ends up being split like this. Okay, so this one will look like this. So a is greater than 2, or a is less than negative 2. And this would be a fine answer. Another way you could write it is you could write it in terms of the intervals that you would have here. So you have two intervals. You actually have negative infinity to negative 2, exclusive, because it's a strict inequality, union 2 to infinity. So this is a way to write it using interval notation. If you don't see that, you could actually just come back here to the inequality and just plot it out on a real number line, right? So I could say I have negative 2 and I have 2 here, and I have to be strictly greater than 2, or I had to be strictly less than negative 2. Okay, and if you have this picture, it's a little bit easier to see the two intervals, right? I see the interval from 2 to infinity, and then union, the interval from negative infinity to negative 2. It's a little easier to visualize it that way. Okay, and that's the pre-image of t. And one last thing I just wanted to remind you of, you probably saw this in your previous classes like algebra, pre-calculus, so forth. If you have functions, especially functions of real variables, right? So these are functions from R to R. Then you can typically do the basic operations on them, right? So I can add functions just by adding, normally subtracting them. I can multiply functions, and I can divide. Now, the division might change your natural domain of the function. For example, I can't make the denominator, I'm not allowed to have the denominator 0, so you have to be a little bit careful in those situations. And if there are real numbers that make the denominator 0, you got to make sure you're excluding them from your domain. But just wanted to remind you other ways you can build new functions from old ones, right?